I think I might have left it at the restaurant. We can go on. I'll get it for a break.
Welcome back to the afternoon session. Let's get started.
Thank you. I'll just make one comment related to Raghuram stock at the end of this one. There's a question I asked him and his answer, and how is it something novel? So I asked the formula for the where any random we take a function was going. I think he said it goes to this integral there, and because given somehow by this integral. On the first form. So in fact, yeah. The thing that I want to say is that this is a very natural generalization in rank n. And so it was the unfolding the rank derivative that I was talking about. So you take P. So yeah, you take K.
That's not the Whittaker.
Sorry.
You take Whittaker into this.
So you take K and number P. I'm gonna explain the more general setting. It's one of the possible generalization with adhering K. And so you take P Caspidal representation. Of GLNA. And pi prime of Gn minus 1a. So in this case, n would be 2. And so you take, yeah, maybe the first thing to say is that if you have pi custom in P, you can associate with, and so you take psi character of this group. That is a character. So you can associate with when we take a function W pi psi of G is going to be given by the integration of over this compact quotient psi and G psi n my psi n from previous lectures. And then the custom has a Fourier expansion. So you have a phi of G's, which is the sum for gamma in this quotient, Gn minus 1k, and right, sorry. Yes, n minus 1k. W phi psi n gamma G. So this is the Fourier expansion of this form on GLN. And so you have a similar thing for P prime in phi prime, we can define W phi prime maybe psi minus 1, okay?
Gamma inside is like gamma 1.
Say it again.
Your gamma is in GLN minus
Yeah, GLN minus 1.
gamma inside the article. W phi gamma G, that gamma is like gamma 1. The diagonal.
Yes, yes. So yeah, the way I embed GLN minus 1 inside GN is by G goes to diagonal G1 there. That's what you were saying, right? Okay.
So this is modulo n minus one or n.
N minus 1, sorry. And so basically what the generalization of this, if you integrate maybe against the character of GL1, you can consider this integral there. Is going to be over Gn minus 1 a Gn minus 1 k phi of G1 phi prime G determinant of G to the S minus 1/2 Gt. So right, this is I phi prime. And so this is in fact a replicated vertical for Gn minus 1. And the using the Fourier expansion and unfolding in this easy case that I was looking at, you find that it is equal to I S W phi prime W phi prime psi minus 1, which is integral over Gn minus a n minus a of W phi G phi W phi prime G1, sorry, n minus 1 G dg. And so here you recognize by local uniqueness of Wheeler models, this integral is Eulerian and it's just a product of both bases of the number P of the local integrals that are already defined. And so yeah, so my only exercise would be a proof this for any proof. Sorry, in this case.
You should still carry the S there, right?
Where do I miss an S? Oh yeah, sorry. Yeah. So determinant of G the S minus 1/2. Okay, so today I will start by talking on intertwining operators, and somehow in a very special case, it's related to what's called the nominal Shahidi method. You have two main methods for defining analytically a function. One is the replicated group that I talked about, and another one is called nominal Shahidi. And so I'll start by holomorphic sections of induced representations. So I'll come back to my setting since the beginning of my lectures. So you take phi1 p1 in reduce it to GN1 and like in there. And for S and T, I will define sigma bracket S be the following induced representation. So it's going to be what I denoted by N1, N2, Gn, determinant S. Let me dot there by one. And no, sorry. I don't want to induce it. Sigma bracket S is just determinant S by 1 4 times. And so this belongs to, this is an irreducible representation of the standard level.
Determinant S twice, like also by.
Yeah. Sorry. That's over 2 minus it. And then I will denote by 5 bracket S is going to be the induced representation. So yeah, of course here n is equal to 1 plus n2. So to Gn of sigma bracket S. And I will denote by P 5 bracket 0. Okay. So this is at least an admissible representation of Gn, and in fact for almost all S is irreducible. But I don't care that much right now, so let me put the function on G eta S U M K is equal to determinant of G1 divided by determinant of G2 to the S over 2, where U is in the unipotent predicate, U and 1 and 2. It is M and 1 and 2. This is in the AN.
Excuse me, Nadir, what is that letter before UNK? What is the name of the function?
Eta.
Eta.
Okay, and then for it's easy to check that for F and P. Fs, which is by definition eta S is F, belong to 5 bracket S. In fact, F goes to Fs is a Kn module isomorphism. And that's all I wanted to say. So one calls I said that Fs holomorphic section. Okay, so now I want to define standard intertwining operators. So let me denote by W N1 and 2 this matrix. So here I put the IN2, IN1. So here I0 and 2 and 1. 0 and 1 and 2. So that so maybe I just write it W M N1 and 2 W minus 1 is M and 2 and 1. And create the state, right? Send this matrix, this one, changes G2 and G1. And so now I'm going to write down an integral, which as this properly formally makes sense. So take a holomorphic section Fs. And G in Gn. And denote by A sigma S W of Fs the following integral. So here I integrate over U N2 N1. So I reverse the order of N1 and N2. Fs W G du. And maybe I'll put the minus 1 here. And yeah, sorry. And so this belongs to the space of sigma bracket S, which is the same as the space of sigma, right? And so this should make sense somewhere if I can give it a meaning inside D sigma. So let me explain how you give a meaning to this integral.
X is N. It's a stupid question, but you really like N very weird. It's U index. This is N2.
U index N2 N1. I reverse the order.
Oh,
Because
it doesn't look like N at all. But you cannot say anything else, I think.
yeah, I definitely want this function to be left invariant under this. Yeah.
You put W in the notation, but you will never do different W's.
Sorry?
You put W in the notation, but W will always be this W, right?
Yes, yes. So I can show you that.
Sorry, an invitation question. What's a G1 and G2 mean in the determinant?
Where?
G1 and G2 in the definition of data S.
Yeah, okay, yeah, sorry. Yeah, so here M is diagonal.
Oh, okay. What question about what you just wrote? What is what kind of object is V sigma? It's the vector space?
Yeah, V sigma is I have a sigma which is pi 1 times pi 2, which acts on V sigma whenever I have a so V sigma is V1 from V. Nothing okay. And so here I'm just twisting sigma S is just a twist of sigma by an unramified character, so it still acts on the same space, right?
Okay.
Yeah, so then there exists a real number depending on pi 1 and pi 2 only. such that real part of x larger than pi 1 pi r pi 1 pi 2 will imply that this integral converges for f and g.
I'm sorry to drag you backwards, but like Fs is some vector, it's a vector in V sigma, right? And then-
Fs evaluated that this is a vector in V sigma.
and this is. Yeah.
Fs is a function in the induced representation.
Okay, yeah, related this, sorry, yeah. And then you do some non-compact integral, and you said already that like this makes sense to, so it's non-compact, right? So it's not obvious that if you average such things, it's still something in this sigma.
Yes, no. A priori, I would like to this to make sense in V sigma, and I'm justifying it right now.
Okay, this is like
Yeah.
just the idea now.
Yeah. So yeah, so such that this converges for all possible choice of f and pi and g in the end. And so, but what does it mean for a vector valued integral to converge? So this means that for any linear form phi in VH, so it was into and 1. Phi of my integrand there, I won't write it again. U is absolutely convergent. And in this situation, it will imply that there exists a unique W in V sigma such that U into N1 phi of my integral, which I don't write again, is equal to phi of W. And my W will thus be and by definition, my integral is equal to this W and to N1 Fs U is equal to W. So that's the meaning of this vector value integral. Okay, and so then one check that in this range of convergence, A sigma S W of Fs, in fact, is a function which lives in I M N2 N1. N sigma W, let me put W sigma. I will define everything just after introducing the notation. So this belongs to this now, where W sigma is sigma of W minus 1. So W sigma of, so say M prime is sigma of W minus 1 M prime W. So yeah, it's purely formal. You check this by doing change of variables. And so this representation here, I will write it, say, pi w bracket minus s. And I will write pi w for pi w bracket 0.
If the board is going to read their, is the question of what?
From mn2 n1 to gn of this representation of
This is exactly what I cannot read.
w sigma bracket minus s.
And what's W sigma?
W sigma of m prime is sigma of w minus 1 m prime w.
Just pi to tensor pi one.
Yeah, more or less, but it's still acting on it's still acting on v1 times by with this version. Yeah.
It has nothing to do with the W in the previous one.
But there's only one w, it's always the same everywhere.
There's no W there.
No, it's the same. There's only one w in the whole book.
W
So which one? Sorry. Yeah, okay, sorry.
It's V. It's V.
Okay, v0. Yeah, and so the main theorem, I don't know who to attribute it to. But it's well-known theorem. So I'm going to be less precise now. Is that there is a polynomial non-zero such that PQ minus S is sigma S W F T is belongs to C, right? Extends to an element of CQ minus S or any F in I and any G in Gn. And so this gives the meaning, this implies that you can give a meaning to AS in general. From pi S to pi W minus S. Or all S in C may be except a finite number. And by uniqueness of meromorphic extension, these have to, maybe I didn't say it. This is the G intertwining operator. This. In the range of convergence, because G acts on the by right translation. This is clearly in the range of convergence, the Gn intertwining operator. And so the meromorphic extension has to remain a Gn intertwining operator.
So irreducible?
Sorry?
Is that irreducible? Is there an irreducible or Gn?
Not necessarily. There might be reducibility points. But for generically it will be irreducible because I started with pi 1 and pi 2 irreducible.
So generically they're irreducible, and for all except finite number, what's the claim? It's an isomorphism, or it's well defined, or
It's the claim is just that it is a Gn intertwining operator. So in fact, it is
What's intertwined, that can be the zero map.
it could be the zero map, but in fact, it is almost never the zero map.
For example, when they're irreducible, it's never zero, something like this.
This, I'm not sure you can always, because of the existence of this P there, and because this is meromorphic, somehow you can always regularize it at the few points where it might be zero or it might have a pole to a non-zero intertwiner in this
I'm
representation.
just trying to understand what's formally the theorem that
The theorem is that these intertwiners, which are only defined in the range of convergence, admit meromorphic continuations.
and the implication is that this map is what
And the meromorphic continuation, by uniqueness of meromorphic continuation, has to be GN intertwined. And then you can check that it is almost never zero, but I'm not using it.
you're saying this concrete thing defines intertwining, and if somebody is willing to check by hand, one can prove probably it's non-zero in some cases.
Yeah, for all S except a finite number, it will never be zero. And it also might have poles. But in all cases, you can regularize by a good power of S, so that you always get a non-zero intertwiner between this and this, more or less.
So what's I guess, the purpose of this theorem? Is it just saying that we have this, we can construct this operation, or?
Yeah, the purpose of this theorem says that at least I have another purpose, but it says in particular that whenever those two representations are irreducible, for example, they are isomorphic.
Okay.
But in a concrete way. Provide a little more concrete.
Okay.
But yeah, this is I want to say something else. I'm trying to give another definition of the L functions that are already introduced. So this I can erase. Wait, so intertwining operators and spherical vectors. So now I suppose that phi1 and phi2 are moreover unramified. And then I fix phi0 a non-zero spherical vector in V sigma k and 1 and kn. So this is the line, right? This is V1 k and 1 times V2 k. And then you can check that there is a unique F0 in pi kn such that F0 of in is equal to phi 0, and similarly a unique F0W in phi W. Yeah, so that F0W of phi n is again phi 0. And so if I twist these by the function eta s or eta minus s, they will remain spherical because this function by definition is right k invariant. So more generally, this implies that fs belongs to phi skn and f minus s f0 f0s and f0w minus s. So here you twist by a slightly different eta, but you guess which one belongs to phi w minus s k and at least generically, but in fact, this is always the line for all s. Generically, it's irreducible, so we already saw that it's a line, but you check. It's not hard to check using a Mackey theory that this is always a line. And so then I can apply my intertwiner there, and it will send this spherical vector to this space. It has to stay spherical because it is an intertwiner, so it will have to be a multiple of this vector. This implies a scalar multiple. This implies that A sigma SW of F0s is equal to, so what letter did I use? Say alpha sigma of S F0 minus SWY, where alpha sigma belongs to CQ minus S. And so the following is a theorem, a special case of a theorem of Langlands following Gindikin and p-adic. So Langlands took care of the p-adic case and he followed those two authors who had already done the Archimedean case. And the theorem is that alpha sigma of S is at S of phi 1. So the ones are already defined for yeah, but I will only define them for generic representation. So yeah, suppose moreover. So here I take phi 1 generic. And spherical. And here as well. So both are unramified, right? And so this is the formula. And S plus 1, phi 1, phi 2 change. So now the next question is what happens, don't have a non-ramified representation or generic representations which are ramified. This of ramified generic representations. So I will admit the fact so I take lambda 1 generic, we take a function of 1 by 1. And the same on pi 2. And then from lambda 1 and lambda 2, you can somehow canonically define lambda s I will take a function and on phi s, which varies meromorphically as well. So there's a canonical construction for lambda s or lambda w minus s. So these are really non-zero. And these are also non-zero except for maybe a finite number of values of s. Yeah. Side n. Okay. And so, in fact, whenever you use two generic representations, what you get is generic as soon as it is irreducible. But even when it is reducible, you still have multiplicity 1 of critical functions, even in the reducible case on the induced representation. So yeah, why do I need to introduce Whittaker functionals here? Because I cannot use the spherical vector anymore, and so I need some multiplicity 1 statement. And so, by uniqueness of Whittaker functionals, which we saw, whenever pi s and pi w minus s are irreducible, at least, this will imply that there exists again CS psi in speed q minus s, such that lambda s is equal to this c times lambda w minus s composed with the intertwining operator. Because this is again a Whittaker function. You compose a Whittaker functional with an intertwining operator. It is again a Whittaker.
This gives that its element in q to the minus s.
Because everything is rational in S here. So yeah. I don't try to justify this too much, but it's formal from what I said before, and I didn't define those two Whittaker functions. But they define in such a way that they're also rational in some sense. And so the theorem of Shahidi is the following. So this is called, this proportionality constant is called Shahidi's local coefficient. And so he computed it in terms of local function. Maybe there's a sign or something, not entirely sure, but CS psi is equal to gamma s pi 1 pi 2 ch psi, where this is equal, which is by definition equal to this quantity which I already defined. Times
Comments?
Sorry?
Put commas, this means like a tensor product of the Bell parameters. Like in L.
Yes, yes,
so
yes,
in
yes.
example,
This how we
commas,
talk. Yes.
This is like a tensor product of the Bell.
Yes, on the gamma side, I always talk about this in my last lecture. If you consider the long-loss parameter of phi1 and phi2 change there, the corresponding gamma parameter is just the epsilon s of the tensor product. Same for cell functions. And so just a word about the proof. Sorry?
Because I the epsilon factor right side.
In the spherical it was S and S plus one. And here you have like one.
Yeah, but
minus
it's not the same thing. It's not the same thing because here I'm adding those Whittaker functionals. So the proof is that in the spherical case, you can compute thanks to the previous theorem and the explicit description of the Whittaker functionals.
Can you say in the spherical case, this orally you find like one thing or something?
Sorry?
In the spherical case, this gamma thing is. What is it like?
In the spherical case, the L functions are already give a formula, and so you also have a way to compute epsilon factors of unramified representations, and it boils down to computing epsilon factors of just one unramified character of GL1. And then it's one, right?
But the sound factor is just one
In the unramified case.
Yeah. So, my question is this formula correct such as in the ramified case?
Yes, yeah, okay. So yeah, because in the
Because
title,
the
okay, in the
ramified-
title, so this is for all. Yeah,
General case. It's
yeah,
not
this is
like-
for all.
Okay, that was my question. Thanks.
Okay. And so unramified case follows from a previous theorem. And then one uses a local global argument. When you have such formula, a nice formula which is valid for all unramified places, sometimes you can deduce it for all places by using such tricks, so local global argument. So basically, he starts with the custodial case, but I didn't define what the custodial representation is. And he globalizes this custodial representation as a local component of an automorphic representation at a given place. And you can even do this such that at all other places, the representation that you get is unramified. And so this gives you the formula for custodial representation. And then by definition, those local coefficients, they naturally have what is called the multiplicativity property, from which you deduce it for any generic representation. Okay, so I have 10 minutes left, or yes. Yeah, so that's all I'm going to say about the local non-linear heating method. And so I will say a few words about the representation which have a vector fixed under the Iwahori. No, so unrelated. RGM IN. So what's IN? IN is Iwahori, so it's another kind of parahoric subgroup that Mladen considered this morning. So it's a subgroup of GM given by matrices of the form OF star OF star. or F PF. So another way to see it is that you have a natural surjection from GLN of F to GLN of AF. And here you have the Lorenzo group of upper triangular matrices. And this is the pre-image. So this is the Iwahori subgroup of GLN, and the Iwahori Hecker algebra is by definition this one. And so X on PI or all V in RG. So it's a much bigger algebra than the spherical Hecker algebra. It's not commutative in particular. And so there's a way to describe it in terms of generator and relations, but this I will not talk about. I will say some other things more related to representation theory. The smooth representation of GN. So yeah, first of all, what does this look like? So for inside GLN, I have a Sn, which is a normalizer of the torus divided by the torus, which we can represent it by permutation matrices. And so let me call this Wn, the wide group. Then I can look at what I will call the affine wide group, which is the group generated by Sn and a matrix like this. So I n minus 2. So here I'll put Wf minus 1. And here I put maybe I want this one to have determinant 1. Yeah. And so this turns out to be what people call a Coxeter group. And so is Wn. These are groups generated by involutions with. Yeah.
The inverse there or you?
Yeah, so here I put two things. Here I put uniformizer to the power -1, and here I put minus. I want the determinant to be 1 basically, so n plus 1, not sure. Omega. Yeah, sorry. And then I can consider this group, which I will denote W and theta, which is generated by the affine wide group, and an extra matrix, which is the nth root of the uniformizer. It's like a cycle matrix, but instead of putting 1 there, I put the uniformizer. And so, in fact, it is isomorphic to a semi-direct product. And so, Gn is the union of over W theta In W In. So it's called, I don't know, the Ruai Iwahori decomposition. And so at least if you take the characteristic functions of such elements, you get the basis of the Iwahori Hecker algebra. Yeah, and so in fact, GLN is not very good for this. The best group for this kind of stuff are simply connected groups, such as SLN. And so in fact, up to modifying the permutation matrices so that they have a determinant one. This would be really the affine by group of SLN. And you have the same decomposition for SLN. You replace by intersection of Iwahori with SLN here, and then you really replace this group there by.
You're saying that for SLN, we don't need the tilde.
Yes. 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 Yeah, I think the first paper, which did this was Iwahori and Matsumoto, and is for simply connected groups. And then it was extended by maybe Brewer and Tins for group or reductive groups. So okay, now let me denote by last thing few things I want to say. So let me denote by RGN, IN. I don't know how usual this notation is, but it's going to be the representations of GN, which are generated by their Iwahori fixed vectors. And so the first fact is that this is the same thing as a category as the modules over the Iwahori algebra. And at least in this direction, you send B to VR. And this is an equivalence of category. So in this case, this is due to Borel and I'm not sure Borel with someone. Sorry, I'm not an expert on these things, but there are very far generalizations of such things. Which is now called the Bushnell-Fusco type theory, representation theory of p-adic groups. And so this is called the Bernstein block. Of the category of smooth representation. Sorry?
Really was more than this. This is general still, it's, even for an open compact, you had this.
Say it again.
You take any open compacts and take this K invariance, then you get a module for that.
Yes, but no, I'm saying this is an equivalence of category. And
yeah, that's okay. It's just Borel. Borel's invention is big.
so for Iwahori is just Borel. Okay. Yeah, and so I just said Bernstein block. So Bernstein block satisfies a bunch of properties. So I'm going to state some of them quickly. So for example, whenever you have P in RGN IN, then all subportions of P are also in RGN IN.
You mean
Could be of infinite length. Whenever you have P in RGN, you can decompose it as P is equal to phi I plus phi prime uniquely, where this is in RGNIN. And so this is a direct factor of the category of smooth representation. Is equal to 0. So phi prime has no Iwahori fixed vector. And I'm going to say two more things. Maybe two more things.
In addition, any constituent that pi I has evaporative.
Say it again.
Any constituent of pi I has evaporative variance in addition. So then you can take pi prime to be zero in what you wrote formally.
Yes.
So that's not what you mean.
Exactly.
No, I can take pi prime 0. There's no
Pi is an
problem.
arbitrary smooth thing, and the pi lower I is supposed to be in the Bernstein block.
Oh, so the Bernstein block has a property that any.
It's a direct factor in the category of.
Has invariance of the expand like sure, okay, sorry, yeah.
Yeah, and so finally, if pi is irreducible and is in the Bernstein block corresponding to the Iwamoto subgroup, then there exists a chi unramified character of the n such that phi embeds into I n, g, and chi. And so maybe examples, and I will stop here. Two examples, three. So of irreducible representations in this Bernstein block. So we already saw the pi guide, irreducible pi guides. Because of clearly they are kn invariant, so they are in invariant. And in this case, the injection is an inequality. Other example is the trivial representation. And so here you can check that it embeds in ITN, GN. So here it's a sub, so I need to put 1 minus n over 2 there. Blah, blah, blah. N minus 1 over 2. And last example is what is called the Steinberg representation, which embeds inside IT and GN. You just reverse the order of the absolute values in the unramified characters. N minus 1. 1 minus n over. Yeah. And so I will stop here.
Point here is that example tells you that the maximal compact doesn't have the same beautiful property as we want.
Absolutely. So the trivial representation of I is called the type, the Bushman-Kusko type, whereas the trivial representation of Kn doesn't have those nice properties.
So
So
which property?
The induced representation there has a k-fix vector. The trivial has, but the Steinberg doesn't have a k-fix. So all subquotients with a k-fix vector in other things.
also I didn't talk about capital representation yet, but having for example irreducible representations, having a new Orley fixed vector determines your cuspidal support to inertia. And it's not the case for Kn.
The property that any Iwamoto spherical representation, you can always put it as a sub in something by rearranging the character. This is something very specific for the Iwamoto, or it works more generally for Bernstein blocks?
Yeah. For Bernstein blocks, Bernstein block is determined by an inertial class of cuspidal support. You know what the cuspidal support is, right? If you haven't read, I'll say more about this in the last lecture. But so, yeah, Bernstein block is always a similar property. Not only the one determined by. Wow.
Actually, this property that Laura mentioned, that's very useful for eigenvarieties. Because, no, because, yeah, typically you want the property like this, yeah, to carry on. Yeah. I think if I can give some example.
You think I can that's into like an integer representation?
I'm saying like when you put it to working forms in a family.
Yeah.
Usually,
Like a P wants them to be induced, like be embedded in some induced representation.
no, it's more like you want to, you know, for example, that the Gauss representation would behave nicely. So you would know, for example, what's say like the cuspidal type, and this will say something that they have like Ivahori invariants. It will not tell you that you have spherical invariants, like having be like trivial inertia. That's a good property that behaves well in a family, and that would mean that it has whatever representation it comes from, it will have Ivahori invariants. It's a little bit maybe premature, my remark, but I'm just saying, like, maybe just remember this.